4.3 continued. Let's look at the first derivative test. So let f be a function defined on AB and continuous on the interval I. Let's suppose C is a critical value of f on I. And critical value means, of course, that f prime of C is equal to 0 or f prime of C does not exist. And just a little subtle thing here, never say equals does not exist. That doesn't make sense. Equals is a number, so you just say f prime does not exist. Don't say equals here. Okay. Then A, if f prime changes sign from positive to negative at C, like around C, then f has a local maximum at C. So we say then f has a local maximum at C. So f of C is a local maximum. Okay. B, similarly for minimum, if f prime changes sign from negative to positive at C, then f has a local minimum at C. So it has a local minimum at C. F of C is a minimum value for the function, in other words. And then if it doesn't change sign, then there's nothing. So if f prime does not change sign, then there is no local extrema. We'll just say then no local extrema. Or extremum, sometimes they say. And we'll see that possible example as well. So, and usually it means something if you have a critical value, but it's not necessarily a local min or max. It just is something else entirely. Okay, so let's look at a number of examples. We'll get through a couple, and then we'll probably do a whole nother video because I have 4 of them I'd like to get through. We'll see how it goes. Okay, first example is pretty simple, but it builds this concept. All right, so let's keep that up for now. So given, I need to change that, huh? Go back to this one. All right, so given f of x equal to x cubed. So let's investigate x cubed with our stuff we know. So we know what x cubed already looks like. So let's just graph x cubed. You should know x cubed, x squared. With a little thought, x cube root of x, you know, that kind of stuff. But you should know x cubed and some of these basic shapes of many functions. So x cubed comes up like this. And then goes like that. And I probably came back on itself too much over here. So I'm going to erase some of that. Okay, so there's my cubic function. So something like that. So that's my y equals x cubed. All right, so if you just start investigating this, so given, well, let's investigate. I'm not going to say find anything because let's just investigate what's going on. If I do f prime, I get 3x squared. And then you're basically going to just set those equal to 0 and solve. So if we set it equal to 0, we get x is equal to 0. Like that. So our critical value, we have just one critical value is x equals 0. All right, so does it change sign at 0? Well, if you investigate f prime of x is equal to 3x squared. That's always positive for all x in the reals. It never changes sign. And you can see that by the graph, right? From left to right, it's always increasing. Okay, so there's no local extrema. So there's only one critical value. Local extrema always occur at critical values. And then this allows us to test to see if it is a local extrema, right? It's all building on itself. So therefore, no local extrema. So it just kind of describing stuff here. If you put an interval, you know, from A to B, then your extrema would be on the closed interval. Then that always occurs. Your minimum would be on the left side, your maximum would be on the right side, right, at the endpoints. Okay, but we're not looking at that right now. But keep that kind of stuff in mind. So no local extrema. But just for future reference, what is happening at 0? Like, what's going on there? Basically, what does f prime of 0 tell us? Well, it tells us that there's a horizontal tangent like that, or that the slope right at 0 is 0. So it's not really it's not like a tangent line. But right at 0, we get a slope that's 0. But it doesn't, of course, change. Okay, so, but the graph does look different, right? The graph looks different. So that is a special value right at 0. Okay, so the graph is kind of going down like this. And then when it changes right at 0, the graph is kind of opening up. That means something. Okay, we will get to that. I don't think until next section, actually. Okay, so that's it. So I just want to investigate that. Next question. This will take a little bit longer. Let's look at this example. If f of x is equal to x cubed plus x squared minus 5x minus 5. And so this is the cubic, so it's still going to have the same basic shape going down on the left, up on the right, because this is positive and this is odd. And it's going to do stuff in the middle. Just kind of getting ahead of ourselves a little bit. This is not always easily factorable. But if you recognize how you could factor this one, it's a special case. So we will be able to factor this and find intercepts. What are my directions here? Okay, so if that, then A, find the intervals on which f is increasing, decreasing. So find the intervals of, and I'll start abbreviating a little bit, increasing and decreasing. B, find local extrema of f. So find local extrema, which is tied to A and B, of course. And then sketch. So C is sketch the graph. So sketch the graph. And indicate intercepts. Always got to do intercepts if we can. So label, intercepts, that kind of thing. Okay. So if you don't know what to do and you weren't able to study, just start taking derivatives. That's really what you can start doing. So just, if all those fails, it just makes you feel better. Just start taking derivatives and see what happens. Take derivatives, set them equal to 0. That's pretty much what we'll be doing. So so basically set f equal to 0, f prime equal to 0, later f double prime equal to 0, and that'll get you stuff. That's basically what we do. All right, so you get 3x squared plus 2x minus 5. And then you set that equal to 0, but we know we need to factor it, so let's just go ahead and factor that. That's 3x and x. It's got to be 5 and 1. So let's see, 5 and 1, and then the difference is 2, so there you go. That's negative and that's positive. Difference is positive. Okay, so that implies, oh, we'll set that equal to 0. And so that is equal to 0 if and only if x is equal to, what, negative 5/3, negative 5/3, and 1. Okay, so those are the critical values, the only critical values. So I mean, that's kind of implied. So it's a polynomial. Everything's defined. It's on the reals, so nothing undefined. We'll look at that next example. Okay, so those are our critical values. We'll be doing first derivative test to figure out increasing, decreasing, all that. Okay, but we also want to find where f is the intercepts. So this is where I like to just get these out of the way. So let's factor x cubed plus x squared minus 5x minus 5. Now this is, again, a special case of factoring. You can't always factor a cubic real easily. But do you recognize what this is? So you have something in common here, something in common here. This you can factor by grouping. So you can factor out x squared, and you're left with x plus 1. Factor out a negative 5, and you're left again with x plus 1. Okay, so that's going to be x plus 1 times x squared minus 5. And then you'll set that equal to 0 and solve. And I'm going to bring over f all the way so that I can just say equals 0. So equals 0. All right, so, oh, and if you had imaginary roots here, like if this was a plus, then you just, those don't show up, of course, on the graph. So you just ignore it. Although it does make it 0, but we're looking at real numbers that make the function 0. We ignore the imaginary cases, but these aren't imaginary. Okay, so our roots, intercepts are negative 1 and what, plus or minus root 5. All right, so that will just plot on the graph when we graph it. So next, we want to apply the first derivative test. First derivative test. And you can do this in different ways and be organized in different ways. This one, I'm going to show you this way, and then the next example I'm going to do maybe slightly different, just kind of analyze it. Just to show you different ways of organizing. So this one I'm going to be like the book, how it did it organized. So we're going to write down an interval. Then we're going to pick a value for k. And then we're going to calculate our test value, which will be f prime of k, like within the interval. Then we'll write down the sign of f prime of x, and then the conclusion. So our intervals are, let me bring this down. So we're looking at f prime, 3x plus 5 and x minus 1. So the intervals are around that. So you go from negative infinity to here, negative 5/3, and then negative 5/3 to 1, and then 1, and then approaching infinity. Those are the intervals we're testing to see if f prime changes sign. So our intervals are, oops, I kind of want to bring closer anyway. Excuse me, negative infinity to negative 5/3. Next interval, negative 5/3 to 1. Next interval is 1, and then approach infinity. Okay, and then we like to put a little chart around this, or box of some sort. I think that's straight. And then down. Close enough. And you don't have to do this chart. This is just, or even like draw the lines, but I want to make it look nice as possible. This time. Okay, and then we pick test values inside those intervals. So within, between negative infinity to negative 5/3, a nice one to pick would be like -2. And then negative 5/3 to 0 to 1 is 0. Obviously, 0 is easy to pick. And then 1 to infinity, you could pick, 2 or 10 or 100 or whatever. Okay, just because you don't always have to evaluate it. You interpret it to see what's going on. I will actually show you numbers this time to be more a little concise of how I'm analyzing it. Okay, so within that interval, I do a test value to see whether f prime is positive or negative. Okay, so I'm actually going to evaluate f prime. So I'm going to show you what I'm doing here. I'm going to plug in that value into f prime and see what I get. So f prime is up here, and I'm not going to show you what I calculated, but you calculate f prime here, and then you write it down so you know what it's saying. So f prime of -2 is 3, which is positive. So it's positive. So what does that tell you about whether it's increasing or decreasing? We'll get to that in a second. I plug in, substitute in, and evaluate at 0, the derivative, and I get -5. That's less than 0, so it's negative. And then f prime of 2, I evaluate, I get 11. And it'll be obvious if you put in even bigger values. That's greater than 0, so it's positive. So it looks like I'm changing sign. So if the derivative is positive from negative infinity to negative 5/3, then I know that my function's increasing. Went from increasing, and then negative means decreasing, and then again increasing. So I went from increasing to decreasing. So what does that tell us about the function? Oops, sorry. So first derivative test is saying if f prime changes sign from positive and negative, I have a local max. That's exactly what it's telling us. Okay, so our conclusion here means I have so it's all local, but it's a local max at -5/3 because it went from increasing to decreasing, right? Increasing to decreasing gives you that max. And then decreasing to increasing is a minimum, right? It goes decreasing and then increasing. That implies a minimum. So it's a minimum at 1. So what we can say then is we have a local maximum f of negative 5/3. When you evaluate, you'll get 40/27. And then we have a local minimum at 1, or f of 1, which is negative 8. Okay, the next thing is to graph that. Okay, so we're going to graph it down here. And we label in all those points. So you're going from, so we also know basically what the function looks like. It's a polynomial. So it's going like that because it's a cubic. This is all college algebra stuff. This is odd, so I know it basically starts up and goes like this, or starts down and goes like this, one or the other. But since this is positive, I know it basically mimics the cubic function. But these other terms basically make it oscillate a bit. And we know exactly how it does that. It's increasing all the way to negative 5/3, like this. So it's increasing, and then it's decreasing, and then it's increasing. So we just got to label all the points appropriately. Okay, so instead of going through all those little details, I'm going to copy it over while you are graphing it. Okay, so try it and graph. Okay, so I'll go and copy that over. Should be right there. And we're just going to squeeze it in here. And then just zoom in on it so you can see it. Okay, so that's what my graph looks like. And you can see the points. So it's it's increasing all the way to that first value at negative 5/3, and then decreasing. There's the intercept right there, y-intercept, all the way to negative 8 at 1, and then increasing, and there's another root, and then it goes up like that. Okay, so again, label negative 5/3. Your roots are negative root 5, negative 1, and root 5. And then here's 1, right, is a minimum at 1, so let me label that. And that's what your graph looks like. Okay, so these are your local min and max. Okay. Next one. Okay, we'll go ahead and do another video for that. We got a few more. We'll do 3 more in a row.